Here we have a 3 kilogram block is sitting on a ramp. That ramp is inclined at an angle of 30 degrees. We're given the coefficients of friction between the block and the ramp. We want to find the minimum force F that is applied horizontally to the block in order to cause it to move. So if we're looking for a force here, that means that we're going to be using Newton's laws. That means that we want to identify the forces, and we'll follow those steps. First, we'll draw a circle around the object. We'll identify points of contact. I have a general force here, my force applied, or I'll just call that F. I have another point of contact along this surface. Whenever I have a surface, I always have a normal force perpendicular to the surface and a friction force parallel to the surface. In this case, we want to find the force in order to move the block. That means that we have to overcome static friction, and that's where we're going to be focused. And then we also have weight, the force due to gravity on this block. So we've identified the contact forces. We've identified the non-contact forces. Our next step is to draw a free body diagram. We're going to start by drawing axes. Those axes are going to be tilted so that they match the direction of the incline. We want to line up our axes with our acceleration. So there's our X and our Y axes. Here's the particle representing the object. These axes are going to be tilted at a 30-degree angle to match the 30 degrees that we have down there. Now we'll go ahead and put these forces on. We have an applied force acting to the left. We have weight that's acting straight down. We have a normal force that's acting perpendicularly to the surface. And in this case, if we are applying a force pushing to the left, then if we push hard enough, we're going to make the block slide uphill. So the block is going to tend to be moving uphill. If we're just applying just enough force to break it free, then we should be moving uphill, and the force of friction should be acting downhill. That would be the maximum static friction, would be just enough to hold us in place, and just as we're applying that minimum force, we'd be overcoming static friction and the block would start to move. If we applied more force than that minimum force, we would just push through static friction very easily, and the block would accelerate easily up the incline. What we want to do here as well is we have several forces that aren't aligned with our axes, so we want to break those into components. So in this case, we want to look for components parallel to and perpendicular to the axes. And the same thing with this applied force. I'm looking parallel to and perpendicular to those axes. I'll call this Fx and Fy. Now I'm using Newton's second law, F equals ma. In practice, this usually means sum of the forces in the x direction is mass times acceleration in the x direction. Sum of the forces in the y direction is mass times the y component of the acceleration. So I can sum up my forces in the x direction. In this case, I have Fx is acting in the negative x direction, it's acting upwards. I've got the maximum force of static friction acting against me. That's in the positive x direction, that's acting to the right. And I've got the x component of the weight that is also acting to the right. And in this case, the acceleration is 0. If we are just barely getting the block to move, our acceleration is just 0. And if we push just a little bit harder, it'll be enough to get the block moving. Looking in the y direction, I have the normal force, that's upwards. I have the y component of the weight, that's downwards, that's negative. And in this case, since I'm pushing the block into the incline, I actually have a y component of the weight, of the applied force as well. And the acceleration in that direction is 0 also. Now I can go ahead and start simplifying. The x and the y components of my applied force seem to be two different terms, but in fact, they're both components of F, the minimum force. That's what I'm trying to find. They both are based on that 30-degree angle. So what I can go ahead and say here is that Fx is F cosine of 30 degrees. The maximum static friction is the coefficient of static friction times the normal force. And the x component of the weight would be the full value of the weight, mg, times sine of 30 degrees. Again, this is a 30-degree angle here, and the x component is opposite that 30-degree angle. Altogether, those are equal to 0. In this case, I'm trying to find the force. I know the coefficient of static friction. I know mg, but I don't know the normal force. So I'm going to have to look in the y direction to find that. Looking in the y direction, I have m. I have the y component of the weight. The full value of the weight is mg. The cosine of 30 degrees gives me that y component there. This adjacent side right there, using the cosine. And then I have a y component of the force. The y component of the force in this case is going to be the full value of the force, F, times sine of 30 degrees, because it is opposite that 30-degree angle. I can solve here for n, and then now that I have an expression for n, I can take this and I can plug it in there for the normal force n. Here I've taken my original equation and I've replaced n with this quantity right there. Now I can distribute the coefficient here, and now I can go ahead and plug in values. I know that mu s, the coefficient of static friction, is given as 0.5. M is given as well, that's 3 kilograms. G is 9.8. And sine of 30 degrees, cosine of 30 degrees comes out of your calculator. So we can simplify all these. The only unknown is F. Now I can combine my constant terms, and I can combine my force terms and move them across the equal sign. And this gives me a value of the force, 39.69. This is a force measured in newtons. I have 2 sig figs for the coefficient, 2 sig figs for the mass, and so I'll round this to 2 sig figs as well, and we'll say that the force here is 40 newtons. Is the minimum force. If we apply a greater force than this, it will be sufficient to get the block moving uphill. If we apply less force than this, then friction will be sufficient to hold the block in place.